So now we'll look at direct preference optimization or DPO, which is another way to do RLHF without learning an explicit reward model or even doing reinforcement learning or having like an PPO style RL loop. Now we'll browse through the DPO paper, direct preference optimization. Your language model is secretly a reward model. So for preliminaries, let's look at the RLHF pipeline. So RLHF pipeline consists of three stages: the supervised fine-tuning stage, the reward modeling phase, and finally the RL fine-tuning phase. In supervised fine-tuning, initially you take a pre-trained language model and fine-tune it on high-quality data set based on human annotations of which have like very good completions and on various downstream tasks to obtain a model, and we will call this model by SFT. The second part is the reward modeling phase, where you want to learn a reward model which is able to compare completions and say which is better, and that would be used finally in the RL fine tuning stage. So, based on the Bradley Terry model, the probability that your completion 1 is better than your completion 2 given your input x is just the ratio of like the exponential of the reward for completion 1 upon sum of the same scores for the two completions. So this looks very much similar to softmax, and if you divide the both numerator and denominator by this term, it would become 1 upon 1 plus e to the power r for e to the power minus of reward for r1, like reward for completion 1 minus reward for completion 2. So if we want to train a reward model based on some data sets of inputs and a comparison of like the preferred completions and the less preferred completions, we would want to maximize the log probability of the uh, correct completions or minimize the negative log probability of the correct completions. So for from if we sample from this data set, this term is just the log of sigmoid of y reward of y1 minus reward of y2. So we want to minimize the negative log probability of that in expectation. So the loss for training the reward model because becomes minus expected log sigmoid of difference of the rewards, and where this comes from your training data set of the reward model. Once you train a reward model, basically fit a reward model uh, on this objective, you would use that to train your final policy and using RL training. And the um, objective is to maximize the performance of your policy, which is to maximize your expected returns, and these returns is basically the sum of rewards. And rewards here are basically two types of rewards. One is the you want to maximize the rewards of your completion that you get from these reward model that you have trained, r5 x comma y, and the second term is you want to minimize like some beta time scale divergence of your policy with respect to the pi SFT, basically the reference policy. So you on overall this is the sum of both these terms becomes your reward, and in expectation you want to maximize this reward, which is the RL fine tuning stage. So usually this RLHF pipeline is pretty complex. You want to train a reward model optimally, and finally even in the fine tuning stage, it's an actor critic model, so you need to train a value function as well as a policy, and need to balance the training of both of them to train it in the RL stage. And often, like as in this particular paper, you would have to add some another part to your objective to ensure that the model also does not forget its pre-training stage knowledge. So add some term to your objective there as well. So the main idea of DPO or direct preference optimization is to first write your optimal policy after the RL stage, which is the policy which maximizes your rewards from your reward model while being also KL constrained. Is in terms of your reward model. So they first derive that your pi r of y given x can be written as like the pi reference of y given x times exponential of 1 upon beta times r of x comma y upon a partition function z of x. So the goal of partition function is simply to normalize this across all possible completions so that this itself is a probability distribution. We'll go over the derivation and proof of this parameterization of the optimal policy in terms of your pi SFT as well as your reward model. But the beauty of this is that now you could also write your reward model in terms of your optimal policy. So rearranging the terms, taking the terms apart from the reward model on the left side, multiplying and then taking a logarithm to remove these exponential and then multiplying it by beta gives you the reward model in terms of your optimal policy pi r after the RL KL constrained RL fine tuning stage, and as well as this partition function z of x, as well as your uh, pi reference. Now, based on your Bradley-Terry uh, model, we saw that we were able to write your probability or that you prefer completion 1 over completion 2 in terms of the sigmoid of differences between the two rewards. And if we take the difference between the two rewards for two separate completions, you would see that the partition function gets cancelled, which means that we don't even need to calculate it. This means that the objective of fitting your reward model can be written in terms by parameterizing it the reward model in terms of the optimal policy, and which means that you get an expression for your objective to for training your reward model using your policy model. And that means that if we try to minimize this objective, we would try to train like the best possible reward model, but it's implicit in nature, and since it's parameterized in terms of the optimal policy, we would learn the parameters for your optimal policy. This way you can fit and find your optimal policy using purely supervised uh, training without even doing RL. Now let us see how you can derive the expression of your optimal policy in terms of your optimal reward model. So to train the optimal policy, you had this expression where based on samples from your policy, you want to maximize these rewards, which is the reward from your reward model minus beta times the KL divergence of your policy with respect to the SFT model. So this can be written in this form. You want to maximize these two terms. Since in expectation the scale divergence becomes the log ratio of the two distributions. Now maximizing this is also equivalent to maximizes 1 by beta times of the same expression, and which is equal to minimizing minus 1 by beta times the same expression. So we add like we multiply minus 1 by beta and this max becomes min, and the two terms are shuffled on left and right. So this becomes log ratio of the uh, probabilities of the completions minus 1 by beta times reward of x comma y. Now this second term can be also written as log of e to the power 1 by beta times r of x comma y, and log a minus log b is log of a by b. So this can be written as log of pi of y by x upon pi ref times uh, e to the power 1 by beta r of x comma y. Now, if we want to minimize the log of ratio of two terms, one is pi of y by x, and the other is this particular uh, term. And if we look at this second particular term, it is not exactly a probability distribution. So to make it a probability distribution, we just need to normalize it. So we divide it by a partition function z of x, and which is nothing but for which kind of normalizes this term for all completions y. So which is nothing but summation over all y, uh, sum of all these terms, and that makes it a probability distribution. And since we divided it by z of x, we also multiply it by z of x, and we take it out basically in terms of minus log of z of x. So nothing, all in all, we added two terms, minus log of z of x and plus log of z of x, and the plus log of z of x went inside and became 1 upon 1 by z of x. So now we want to minimize this entire expression, since the partition function is just a function of x, and the policy is responsible for y's minimizing this sum of these two terms is just equal to minimizing this single term, and you want to minimize expectation y is being sampled from pi log of pi upon another probability distribution. So this is nothing but the KL divergence between pi of y given x and um, the term 1 by z and and this particular distribution. So finding the most optimal pi such that the KL divergence between pi and this particular distribution is will be like minimum when pi is actually equal to this distribution. So minimizing this KL divergence is equal uh, finding the best policy of finding the best values of pi, which minimizes the KL divergence between pi and this distribution, is when pi itself becomes this distribution. So which means that your optimal policy, or pi star y given x, can be written as 1 upon z of x times pi reference of y given x into e to the power 1 by beta times r of x comma y. Hence, you can see that we have derived an optimal your optimal policy in terms of your reward model, and uh, on the flip side, we can rearrange terms and rewrite your reward model in terms of your optimal policy, which we use fundamentally in DPO. So now let us look at the equation of the gradient of the DPO update. So it consists of these two terms. So if we look at this term, we want to minimize the negative log likelihood of your um, correct generations, and which is very intuitive. The second part, we want to decrease the likelihood of your incorrect, less preferred generations, and and this term, this difference in log likelihoods, is multiplied by a weighting term, and that weighting term is higher when the difference between the two rewards is high, and is lower when the difference between the two rewards is low, which means that if the more preferred completion is much better than the less preferred completion, you the overall these gradients get a higher weight in the training process. Now let's look at the derivation of these of the exact gradient formula. So now let's look at the derivation of the gradient of the DPO objective. While going through the derivation in the paper, I just noticed that there's a slight error made by the authors. So actually, the objective, like the LDPO, was this term, but these two terms were flipped. So it was like beta times log of pi theta by pi ref for the YW minus the same for YL. So I think the derivation is slightly wrong, and it's just the minor exchange of terms here, probably starting where they made this minor mistake. So we'll see the derivation with the correct terms. So for us, let's just mentally exchange these two terms. So now it is negative. So that was your LDPO. So to find the gradient, we'll take this gradient inside your expectation. Now gradient of log sigmoid of something, we want to find the gradient of that. Now derivative of log of something is 1 by that thing times derivative of that thing. So now the term inside, let's call it u. So what they are saying u here, we would have to just flip the two terms because of the mistake that they made starting out. So it would be basically minus of this, of the term that they have here, and then we want to find like the derivative of log of sigmoid of um, the minus of this term here. So um, derivative of log of sigmoid of u is 1 by sigmoid of u times sigma prime of u, where u is negative of this thing. So, and sigma times the derivative with respect to theta of u. Now, sigma derivative of sigmoid is sigma x into 1 minus sigma of x, and sigma of minus x is 1 minus sigma of x. So sigma prime of x is sigma x into sigma of minus x. Now sigma of u and sigma of u will get cancelled, so it will, the term that remains is sigma of minus of u times derivative with respect to theta of u. Now sigma of minus of this term, now already the signs are flipped, so minus of minus becomes plus. So what we get here is beta times log of probability ratio of YL minus beta times log of probability ratio of YW. So where the probability ratio is like pi theta upon pi ref. So these two terms would be exchanged. I think in this derivation they made it incorrectly, times the derivative with respect to theta of u, where u is negative of this term here. So if we take now this, if you look at this term here, it's log of pi theta minus log of pi ref. So derivative of pi ref with respect to theta, log of pi ref with respect to theta will be 0, since your reference this particular term doesn't depend on theta. So what remains is the difference in the probabilities of yw minus derivative with respect to theta log of pi of l. So basically this term is correct, and the signs of this term should be flipped. So, and the error just came because of the mistake starting out in the original objective for DPO. So that's like the derivation of the gradient of the DPO objective.